All right. Hello there, everybody. This is my favorite part. I don't know if you guys get to see this. I get to see the participant numbers just sort of climb and roll in. This is where I get to imagine you streaming into the venue and taking your seats and speaking to your neighbors and getting all excited about this. But and so I will drag myself away from my favorite part just to say hello, everyone, and welcome. Historically, today is National High Five Day, but I think the pandemic has officially replaced that with National Elbow Bump Day. In case you didn't know, today is also McDonald's Day. Today in 1955, Roy Kroc opened the first McDonald's in Des Plaines, Illinois. And while they are hands down the best French fries, our neocortex has been struggling with whether or not we really should be eating them. And so, welcome everyone to Skeptical Inquirer Presents. This is a series of live online presentations from experts who are devoted to advancing science over pseudoscience, media literacy over conspiracy theories, and critical thinking over magical thinking. My name is Leanne Lord, and I'm delighted to be your host. I am a stand up comedian and author, and I'm also a co host for the Point of Inquiry podcast. If you are so inclined, you can also find out more about me and my work at veryfunnylady.com. Now, before we get going, I have a few reminders. The Center for Inquiry's Coronavirus Resource Center continues doing the work of fact checking misinformation and sharing reliable news at centerforinquiry.org/coronavirus. And some of the articles that they've curated this week include a piece from Wired about a new type of Bill Gates conspiracy theory that is going viral on Facebook. I don't know where folks find the time. I really don't. And an article from the medical care blog about how COVID-19 scams are spreading just as fast as COVID-19, so far to the tune of $397 million. That's a lot of French fries. And as always, I invite you to subscribe to Skeptical Inquirer magazine. There are two ways to do that, both digital and print. And the bonus, the print subscription also gives you access to the digital version. So you can get either and or both at skepticalinquirer.org. And by all means, please, please, please mark your calendar for our next Skeptical Inquirer Presents, which is on Thursday, April 29th. Look, this is the one you don't want to miss, okay? Given the presentations that we've had here in the past and the questions that have proliferated on this topic, you will want to be here to hear Mick West talking about escaping the rabbit hole, how to help your conspiracy theorist friend. Yes, this is the one, everybody. There's hope. Now, if you're new here, here's the deal. The flow of the evening is easy breezy. You keep doing whatever you're doing. I will introduce our guest. They'll razzle and dazzle, after which we will open it up for your questions. And at the bottom of your screen, you know the deal. You'll see this little Q&A button, that icon there. That's the place for you to type your questions in the form of a question. Everybody, don't need the CV for that. And if you miss any of the talk tonight, it is being recorded and will be available on skepticalinquirer.org. All right, everybody. So now off we go. I had the pleasure of meeting tonight's guest in 2019 at SciCon, and I can honestly say that my neocortex has not been the same since. Our guest was elected to the National Academy of Engineering in the early aughts. He directed the Redwood Neuroscience Institute, now located at UC Berkeley. He is a scientist and co-founder at Numenta, a research company focused on neocortical theory. Simply put, it's where neuroscience meets machine intelligence. He wrote the book On Intelligence and A Thousand Brains, a new theory of intelligence, which is the subject of tonight's talk. He is widely known for founding Palm Computing and Handspring and is basically credited with starting the entire handheld computing industry. And I'd like to think I helped with that since I owned and loved the Palm 3, Palm 5, and the Palm M515, you know, doing my part for retail, consumerism, and science. You're welcome. So, with us tonight to talk about how the brain learns and why it sometimes gets it wrong, please welcome Jeff Hawkins. Jeff, you have the con.
Thank you, Leanne. That's very, very kind introduction. Yeah, we met, as you said, about a year and a half ago, and at the SciCon conference in Las Vegas. And the talk I'm going to give today is similar to the one I gave then. It's been slightly modified, but I want to tell a story about that conference because I spoke early in the morning on I don't know one of the days, and Richard Dawkins spoke at the end of the day, and he gave a beautiful and eloquent talk as he always does, and so I approached him afterwards, and I met Richard a few times, but didn't really know him too well. And I asked him, I said, well, Richard, did you hear my talk in the morning? He goes, yeah, I did. And I said, oh, well, what do you think? I'm kind of nervous, you know. He says, oh, I thought it was pretty good. And then I went bolder and I said, well, you know, I'm writing this book and it's not done yet, but would you be so kind to read an early draft? Would you be interested in that? And he said, yeah, I'll do that. So a month or so later, I sent him a draft of this book I was writing. And then a few weeks later, I wrote him again and said, Richard, have you started reading it? And what do you think? He said, oh, I think it's pretty good. I'm about halfway through. And so I said, okay, well, I said, would you consider writing a foreword for the book? And I'm doing this in email exchange. And he said, yeah, I'll consider it. So a few weeks later, I wrote him again. I said, Richard, well, what do you think? He said, oh, I've written it. Here it is. And that book just came out last month, called 1,000 Brains, A New Theory of Intelligence. And the talk I'm going to give today is talking about part of what's in that book. And Richard Dawkins wrote a very, very generous foreword to the book. So that's a little introduction about tying this back to the last time that Leanne and I met, and also when we were at the last real person conference. Okay, so I'm going to talk about brains today, it's a pretty deep topic, but I'm going to make it as accessible as I can. It's going to require I show some images, so we're going to do a presentation on this, and hopefully everyone can follow along. When we get to the end, we'll look forward to doing Q&A. So I'm going to now share my screen, and we're going to get started with this, and hopefully this is all going to work as it's supposed to, like that, and like that, and like that, and I assume everyone can see that. So as Leanne said, that's the title of my talk. And as he said, I work for this company called the Meta, which does sort of neuroscience research. I run a research lab, and we also do machine learning and AI work related to that. And I mentioned the new book, which is here, 1,000 Brains, A New Theory of Intelligence. I'm shamelessly plugging it right now, and once again at the very end of the talk. So let's just jump right into it. Hopefully you recognize this. Everyone has one. It's at least everyone here has one. It's a picture or a drawing of a human brain. And we can roughly divide that into two parts. The one part, called the neocortex, is a big sheet of cells. It's about the size of a large dinner napkin, and it's about 2.5 millimeters thick, so maybe twice as thick as a dinner napkin. And it wraps around the rest of the brain and fills our skull. It's about 70% of the volume of our brain. And those little ridges and valleys are just trying to stuff this sheet of cells into your skull. There's a lot of other parts of the brain, dozens of other regions, and we can just roughly call them older brain areas because they're mostly evolutionary older. And they do lots of special things, and they occupy about 30% of the brain. I mean, you can't see most of them. They're stuffed up inside the neocortex that wraps around them. If we want to say, like, what do these older brain areas do? Well, they take care of a lot of bodily functions, such as breathing, digestion, reflex behaviors, even things like you might think you learn to do, you don't really do, like walking and running and chewing. These are things that are your genes know how to do. We're just born prematurely, and so we don't walk right away. Also in the older brain areas are things like our emotions. If you get angry or sad or someone becomes violent, that's part of these older brain areas. So we can roughly divide it like this. The neocortex, on the other hand, is everything we think about as intelligence. So anything you're conscious of, your conscious perceptions, when you look at something or see, or you're looking at your computer right now, or looking around the room, you're hearing things, you're touching things, that's your neocortex doing that. It's also responsible for all language, and not just like spoken language, like I'm doing right now, but written language, also the language of mathematics, sign language, the language of music. The neocortex creates it and understands it. So right now there are cells in my head that are spiking on and off, creating the movements of my lips and my voice box, which are creating my language. All things we might think of as cognition or thought or planning happen in the neocortex. So all the accomplishments of humans have done over the years, from engineering, math, science, literature, agriculture, you name it, It's a product of the neocortex. So the neocortex is a pretty amazing organ, and all mammals have one, but in humans, it's particularly large relative to our body area, and we are particularly smart. So there's no question about why it's due to the neocortex. Now, the neocortex, interesting, is although it generates a lot of our behaviors, like my speech right now and all the things we do day to day, it doesn't, none of the cells in the neocortex directly control any muscles. So the neocortex can't make any muscles move directly. That is, none of these cells project to muscles. Then the cells in the neocortex project to other areas of the brain, which then can make movement. And so it's not really in control all the time. So if you think about it, like take something as simple as breathing. Well, you don't need to think about breathing. We breathe in our sleep. If you're in a coma, you breathe. I'm not thinking about breathing right now while I'm talking about it, but we could, if I said, okay, we're going to take 2 deep breaths and we're going to hold our breath. Well, we could all do that, and that's the neocortex controlling that. But after a while, the old brain says, you know what, I'm going to need some oxygen, and we're just going to go for it, and we're going to breathe, and you can't stop that. The same thing, it's just, if you might leave your house in the morning saying, I'm going to eat only healthy food today. And so you get to the break room and there's some old donuts and you're saying, well, I shouldn't eat that. But then your old brain smells it and looks at it and you eat it anyway. That's because there's these motivations and drives that the neocortex really isn't in control of all the time. So that's kind of plays a big part of who we are and why we don't always do good things. Now, if we ask ourselves, what does the neocortex do? I should stop for a second and point out, I'm hoping you're finding this interesting. I think everyone should want to know what their brain does. I mean, we are our brain, right? So, and this is what you are. So I think, always hopefully everyone's interested in this because it's important to know who we are. I think it's critical actually. Okay, so what does the neocortex do? You might think it's like a computer and you say, oh, it gets some inputs and processes and do something. That's not right. That's not the way to think about it. The way to think about the neocortex is it learns a model of the world. It literally creates a model of the world in your head. And let's just talk about that. First of all, everything you know about the world is stored in this model. So you've learned what things feel like and what they look like, what they sound like, even simple things. If you pick something up, I often use a coffee cup. I'll use that example today. You have to learn what the surfaces feel like and and the sound it makes when you put it on a table and so on. You do this for everything you know. You have this complex model of the world of what everything looks and feels and sounds like. We also have to learn where things are located. Our brain is not just a list of things. We know where we keep everything. Where do I keep the knives in my kitchen? Where is the chairs in my living room? Where do I, where is the buildings in my town and so on? Everything has a location and the cortex knows this. We also have to learn how things change when we interact with them. Take a simple a thing like a smartphone. Well, it's an object, you can feel it and look at it, but when you touch it, the icons change or make sounds, and you touch another icon and then something else happens, and you push the buttons and so on. Something as simple as a stapler, what happens when you push it down? How do you open up and change the stapler? These seem very simple things, but these have to be stored in your head someplace. And of course, we learned a tremendous number of conceptual things. So we know tens of thousands of things about the world, but we also know things like words. Every one of us knows 40,000 words, and we learn concepts like democracy and fear and humility. And these are things that are somehow stored in our head in this model. And what's the advantage of having a model? A model allows you to do several things. It allows you to know your current situation. I can open my eyes, look around, and say, oh, I know where I am. I can recognize it. I can see now, or I might be in a new place, but I don't know what it is. Oh, this is a restaurant, and I can see where the kitchen is and things like that. But most important, a model lets us to predict the future, and so we can predict the consequences of our actions. Like what would happen if I go down this hallway? What would happen if I turn left? What we'll see if I turn right, and how to achieve goals. And this is where it really becomes an important part of our survival. It allows us to say, given a model of the world, how is it that I might achieve a particular goal, whether it's something simple as getting a bite to eat or something complex like getting a promotion at work, something like that. Now, I found that a lot of people have trouble understanding what it means to have a model. Like, what is it? What do you mean a model of the world? And we're going to talk about it a bit, but I've added a few little slides here I want to talk about just to give you a sense of what we're talking about a model. Here's a picture of a model. This is a model of a house that an architect might have made. It's a physical model. And the reason we do this is that people build models like this is that, again, you can imagine what this building would look like from different angles. You can imagine, you can say, well, how far is it from the driveway to the pool? Or what will my views be from different directions? And how would I plan to do things in this house? And that's how we build a model. But now this is a physical model, and we clearly don't have physical models in our head. But nowadays, a lot of models are built on a computer. So here's another model of a house. This is a computer model of the house, and the same things. You can say, what does the house look like from different positions? How many steps are between things? So I can say, okay, this is one location. What if I was looking down upon the house? What if I was looking from a different angle? Now, how are models like this created? And that's, of course, created in a computer. The basic way that models like this are created in a computer is they create reference frames for these things. So you can think of it like the X, Y, and Z reference frames. Hopefully, you all remember that from high school. And you can locate things like where is the door relative to where is the window and things like that. And objects in like a model like this house. Imagine there's a garage door on this model, and it has its own model. So when engineers create models like this, they say, oh, there's a reference frame in green for the door, the garage door, and it's at a location relative to the reference frame for the house, which is the blue arrows. Now I mention this because surprisingly, this is very close to what's going on in your head. And when I talk about you building models of the world in your head, we're going to see it's something very much like this, and allows you but you're doing it for everything, not just your house. You're doing it for your town and every possession you have and everything you ever interact with. So we're going to go back to our presentation here, and we're going to say, okay, so we've talked about what models are good for. Now there's a surprising thing about our model in our head, and that the model in your head is actually your reality. What you perceive about the world is the model. You're actually not perceiving the real world. You're perceiving the model. I know this sounds weird, but it's true. And I'll just walk you through a little bit about it. You can think of your brain as being in this box, your skull, and the inputs are coming from your senses, like your eyes and your ears and your skin. But how they enter the skull is these little fibers, these nerve fibers, they're called axons, but they're nerves. And they just like a little wire, and they have these spikes coming down the wires, which are called action potentials. You might have heard of spikes or action potentials. And now the interesting thing about it is there's a bunch of these coming from the eye, and there's a bunch of these coming, about 1 million from the eye, and about 1 million from your skin, and tens of thousands from your ear. But they're all identical. The fibers coming into your head, there's no difference between them. You can't look at a fiber and say, oh, this one represents light, and this one represents touch or something like that. Doesn't have that. It's just these spikes. And then your perception, so there is no light entering head, there is no sound, and your perception of what's going on in the world is built up from your model. And it turns out things like color don't really exist in the world. I know you might think they do, but they don't. There's frequency of light, and so on. So we live in this model. The model is tied to the world. It's learned from the world, but we actually perceive the model, and it forms our basis of all of our beliefs. And that's what this talk is going to be getting to. Is about our belief systems, how the brain creates beliefs. So we clearly, our model of the world relates to the real world, but it doesn't always get it right. We'll come back to that in a moment. But everything you believe, all your things you think you know for certain are really part of this model. And if that model is accurate, then they're accurate. If it's not accurate, they're not accurate. So this leads us to the question, how is it that the cortex learns a model of the world? It gets to the crux of what my team does in our research. So I'm going to delve into some more neuroscience here. I hope it's okay. And I don't want to lose anyone here, but I think it's really fascinating. So let's go on. Whoops, I need to click here. All right, so now the next thing we can say is the neocortex, although it looks very uniform, from the outside, it just looks like, I'm going to try to get this thing off my screen. Excuse me for a second. I got something on my screen. It looks very uniform, but it's actually divided into different functional regions. And let's just do that here. So if you look at the human brain, there's some areas in the back of your head that are visual. There's areas on the side of your head that are auditory regions, and the somatic is just the touch region. So this is where the inputs from those different sensory organs come into the brain. And then there's other regions, such as these on the side here, which are responsible for creating language. This is what these are responsible for creating my speech right now, and you're listening. And then, of course, there's a lot of other regions that do more high-level things. They're very difficult to characterize. Now, you might think that, okay, well, the visual regions are doing vision, and the auditory regions are doing sound and hearing. and language doing language and so on, you'd think, well, they must be operating on some different principle. They must be different in some ways because sight and sound and language don't seem the same to us. But that's not the truth. And the truth is very surprising. When people first started looking at the neocortex about 120 years ago, and these are images from a famous scientist, Ramanika Howe. He was the first person to look at the cells in the neocortex through a microscope. And he drew these drawings by hand. It's not a photograph. Those are hand drawings. He did thousands of them. He won a Nobel Prize for his work. And so what he's looking at here, he started looking at the neocortex. And these are pictures of what he saw through the microscope, a slice through the 2.5 millimeter thickness. So this is like a slice of the little dinner napkin, a very small little slice. And what you see on the left picture, those little dots are the actual neurons. Now they're far more than you can see here. This is a very small subset of them. But you can see that the neurons they have different sizes, they're different shapes, and they're different packing densities. And so you can imagine there's these layers going horizontally, and people started talking about the neocortex is composed of layers. The second drawing shows some of the connections between the neurons, and these are the axons and dendrites, and you can see these are mostly vertical, then these are cutting across the 2.5 millimeters, and information flows up and down. Now, this is 120 some years ago. There have been thousands of neuroscience papers, scientific papers, published on the neocortex and its architecture. It's an incredible amount of data has been collected over the decades. And it's hard to even comprehend all the information we know about it. But people like myself, we try to organize this information and try to figure out, okay, what are the different types of cells, how they organize, what are the connections between them. Now, here's an amazing thing. We make these kind of diagrams, but for the most part, these details are the same everywhere. If you look in a language area, a vision area, a touch area, if you look at a cat's brain, a rat's brain, a mouse's brain, they all have a neocortex, you're going to see an amazingly similar circuitry. There are some differences. Sometimes you'll see more of one cell type than another, some are a little bit thicker and less thick and so on, but this incredibly preserved detailed architecture. And this doesn't at first make any sense. How could all the different things that we do be built on the same detailed architecture? Well, the first person to figure that out, so that's the question we're going to answer. The first person to figure it out, or at least suggest a way of thinking about it, was this man, Vernon Mountcastle. And he was a neurophysiologist at Johns Hopkins University. He wrote a famous monograph, which is a sort of a small technical book, in which he made the following arguments. He said, all areas of the neocortex look the same because they perform the same intrinsic function, meaning internally they're doing the same thing. He says why one region is vision and another region is auditory is depending on what you're connected to. So he says if you just take a bunch of neocortex and connect it to the eyes, you're going to get vision. If you connect it to the ears, you're going to get hearing. If you're going to touch it to the skin, you get touch sensation. If you connect outputs of these one section, these different regions of the cortex into other regions, those other regions might do things like high-level thinking or language. And so, which is an incredible idea. And then he said one thing further. He says, well, if we can actually think of the cortex as divided into functional units that are the same. And he proposed that the functional unit is something called a cortical column, which you can think about it as like 1 millimeter in area and 2.5 millimeters thick. And so in this picture, this is a cartoon drawing. You might think about what neocortex might look like. It's this sheet of neural tissue composed of all these little columns stacked side by side. In a human, we would have about 150,000 of these columns in our neocortex. Now, these columns are very complex. Each one has 100,000 neurons, about 500 million connections between neurons, each of these columns. And they're very complex entities. But we have 150,000 in our brain. Other animals have different sized neocortex, and they also have columns, but they're just different numbers of columns. So we got more. In some ways, not always, but in some ways, that's why we're smarter than other animals. So now our question is, well, okay, what does a cortical column do? If we can figure out what one cortical column does, then we can figure out what all of them do. And so this is like a great scientific puzzle, like what kind of function could a cortical column do that can explain vision and hearing and touch and all these other things? And how could you just make a brain out of lots of them, and how do they work together? That kind of thing. So that's what we study. And we made a lot of progress understanding this, a great deal, actually. We have a pretty good idea of what's going on. I'm going to share it with you right now. I'm going to start with a little thought experiment. And so to do that, I'm going to stop sharing. and you hopefully can see me again. And this is a thought experiment that actually happened. This is how we had a real breakthrough here. I was holding this cup. This is a Numenta coffee cup. I hope you can all see that. And I was just idly playing with it. And I had my finger on the side of the cup. And I said, well, I'm touching this cup with my index finger. And I said, if I move my finger up to the top of the cup, I can predict what I'll feel. I said, oh yeah, I'm going to feel this rounded edge up here. If I move my finger to the side of the cup, I know my brain is going to predict I'm going to feel this handle. And if I move my finger to the bottom of the cup, I know I'm going to feel this unglazed rough area at the bottom down here. Now, I know I make this prediction because I can imagine it, but I also know that the brain's always making predictions. And if any of these predictions weren't true, I would notice it. But the question I asked him, well, what does the brain need to know to make that prediction? And the answer was at least partially pretty simple. It said, well, first of all, I need to know I'm touching this cup, right? That's because it matters what I'm touching. You know, something else will feel different. But it also my brain needs to know where my finger is relative to the cup. It needs to know the location of my finger on the cup. And as I'm about to move my finger, it needs to know where my finger will be after it stops moving, because otherwise it wouldn't be able to make that prediction. So it needs to know the location where it is and where it will be when it's done moving as I move. If I move one way, I feel one thing. If I move another way, I feel something else. Now, this is actually something really hard for neurons to do. How could they do this? This knowing where my finger is has nothing to do with where the cup is relative to me. It doesn't matter where the cup is oriented or horizontal, sideways. I make the same predictions. So it's really, I need to know my finger's location relative to this cup, wherever the cup is in the world. And that was a key insight that sort of exploded the whole thing open. So we'll go back to talking about the presentation here, hopefully. And, oh yeah, I can just like this. I should be able to do this and that. Okay. So this ultimately led, after several years, what we call the 1,000 Brains Theory of Intelligence. And that's what the name of the book is, 1,000 Brains. So I'm going to explain what that means. So here is a picture of a cortical column. And I know this is getting deep. Some people, I hope you can all follow this, but I think it's really cool. So we'll bump up again a little bit. So here's a picture of a cortical column. Imagine this one is getting input from the tip of my index finger touching that cup, like I just talked about. And it's just one column, and it's just getting input from a little part of the tip. Now, there's actually two things that come into this column. This is facts. This is not speculation. There is the actual sensation from the tip of your finger, what you're feeling. And then there's a movement command, which basically represent how is the finger or the hand moving. So the column gets to know where the finger, what the finger's feeling, and which way the finger is moving. In internals to the column, I'm going to explain this in a very simple way. It's more complicated than I explained it, but basically this is the right idea. There's two things that are known. One is the column keeps track of the location of the finger in a reference frame relative to the cup, just like the reference frame I talked about in the house. And when I move my finger, the column updates the location of the finger in the reference frame of the cup. And then, of course, there's a sensation coming in, and that goes into another layer of cells. And the blue line here represents how you learn the shape or the feeling of the cup. It basically pairs what you sense with the location of what you sense. Now think about this. I can learn an entire cup just by putting my finger on it. I can put my hand in a black box and touch something, and I move my hand around it and touch it with just one finger. I can learn the shape of this cup or learn the shape of anything. And what you're doing is you're literally moving the finger and you're learning what you're sensing at each location. There is another layer of cells which represent the object, the cup itself. So the object, in this case, the coffee cup, is essentially a collection of locations and sensations. It's like, what are all the things I'm feeling at these locations? Now, and so you can learn a model of a cup. So this is pretty impressive. A single column now, this one little piece of the neocortex, touching one little finger, can learn the entire model of a coffee cup, what it feels like. So columns, the basic idea is that columns create reference frames for every object they know. And the reference frame is used in the same way I mentioned it before. It specifies locations of features. It can use it to predict the outcomes of movements, like what will I feel if I move my finger. It allows us to plan to achieve goals, like how do I reach, if I want to reach and grab the handle, which way direction? If I want to stick my finger into the liquid in the cup, which way do I go? And our modeling and simulation show that a single column can learn hundreds of objects in a very sophisticated way. So the second part of the 1,000 brain theory is that there are thousands of complementary models for every object. If I said, well, where's the knowledge of a coffee cup in my brain? It's not one place. It's in many places, in many columns. It's not all the columns, but in thousands of columns in the cortex know what the coffee cup thinks about. Here's a simple way of thinking about it. Here is a picture of a hand touching the coffee cup. And let's say we're using 3 fingers at a time, right? So there are 3 fingers touching the cup. Each finger is at a different location. Each finger is feeling something different. And so each column is going to model, there's 3 columns associated with the fingertips. Each is going to try to learn to model that object. And they can do that. And so they can, but now there's something else that can happen. And because they're all touching the same object, in this case, they're all touching the coffee cup, they should agree on what the object is. They should say, yes, we all know this is a coffee cup. And they do. There are these long range connections in the cortex between certain layers, which we believe are voting. It's the ways where the columns are saying, well, I'm touching an edge, it might be this or that. And someone else is saying, I'm touching this surface, it might be this or that. And someone else is saying, I'm touching something else, I don't know what it is. But they can all get together and they can say, the only thing that makes sense here is a cup. And they very quickly resolve this and say, we're all touching a cup. Now you can think about this. If I were to ask you to recognize an object by sticking your hand in a black box and touching it with 1 finger, well, then you'd have to move your finger around it a bit to feel what it looks like. But if I grab it with my hand all at once, often you can recognize it with a single grasp. That's because the columns are voting and they don't need to move, or at least they'll need to move less. The same thing is happening with vision. You may think vision feels like a different type of sensation, but it's really not. In this case, there is you could think about the back of the retina is an array of sensors, just like the skin is an array of sensors. They happen to move together, but that's not that important at this time. And what happens is that each of those little patches of your retina project to a cortical column in your neocortex. So when you look at something, you're not really looking at a picture of it. You're actually looking at lots of little pieces. Each piece in your brain is keeping track of where it is on the object you're looking at. And when you look at something, you say, oh, that's a cat or that's a dog, all those columns vote together. If you looked at the world through a straw, so imagine you had a very skinny straw and you could only look at the world through a straw, well, then you wouldn't be able to see much at once. You'd only be activating our 3 columns and you'd have to move the straw around just like you have to move your finger around. So it's very analogous to what's going on with touch. Okay, so the interesting thing about this is what do we perceive? It turns out that the only part of this system that we can perceive is the sort of voting neurons, the object in some sense. So when you look out at the world, it seems stable. If I'm looking at a coffee cup or I'm looking at a person or I'm looking at a refrigerator or whatever, my eyes are constantly moving. They're moving about 3 times a second. Everyone's eyes are moving about 3 times a second. They're jumping this way and that. They're called saccades. You're not aware of it at all. The world seems stable. You don't think that the inputs are changing. What's going on is the inputs are changing to your brain. These columns are all jumping around, looking at different locations, different sense features, and yet they're voting on the same thing. It's still the refrigerator. It's still your friend. And that is the only part of the brain we can perceive. We can only perceive the operation of these voting neurons. So we're not aware of what mostly is going on in our brain. We're not able to perceive all these crazy things that are happening underneath. We're just perceiving what's the consensus vote of what's going on out there. And this is important because this is why we have a singular sensation of the world. This is why we don't feel like we have thousands of models operating independently, voting, trying to figure out what's going on, is because we only perceive what they agree to. And this is something that some of people may have heard of. It's called the binding problem. Like, how does the brain bind all our sensations together? It doesn't seem possible. And the answer to it is that the columns vote, and we're only able to perceive the voting. So that's a pretty interesting thing about that. Okay, so now let's talk about knowledge in general. And I'm going to claim here that all knowledge is stored in reference frames. So again, this is the idea that if the entire neocortex is working on the same principles, then everything we know must be stored this way. And so it's like everything is stored in reference frames. And now that's a sort of deduced operation, but it's true. So now we can think about a column as a generic column. Let's say someplace else in the cortex doing math or talking about history or something like that. And so you can think of it as, okay, well, there's inputs to this column. These inputs may not be coming from your senses. They be coming from other parts of the brain. They may be objects you recognize or other things you've already perceived. But those are the inputs to this column in this other part of the brain. And the movements in this case are not physical movements of the body necessarily. It's sort of the same idea. It's like mentally moving through space, just like you can imagine mentally moving through your house right now. I can say, well, we'll go in the front door and look right and look left. What do you see? So what we're doing is when we're accessing knowledge in our life, we're mentally moving through reference frames, recalling the facts that are stored at different locations. Now, you're not aware of this. You're not thinking like, oh, my knowledge is stored in reference frames. No, you're not aware of that at all. It's just some ideas, these concepts pop into your head. But what's going on underneath is that you've stored all your knowledge in the world in these reference frames, and you're moving around and getting them. This is important because it makes knowledge actionable. Our knowledge of the world, again, is not like a list of facts. It's stuff we can think and reason about. We can say, oh, what about, think about, evolution. What do I know about it? How does it behave? What would I do if I change the way this gene works, and so on? Knowledge becomes actionable because we've arranged it in reference frames, just like the knowledge about a coffee cup is actionable because I put it in a reference frame. And now thinking is what occurs when your brain moves from location to locations in reference frames. As we think during the day, these ideas sort of pop into our head all day long, just constantly if we're awake. And what's going on there is that literally the cells in your neocortex are accessing different locations in these reference frames, moving from one location to the other. And when it moves to the reference range, it recalls some fact, and that fact pops into your head. And that's what we do when we think. Now, here's an interesting thing. You can take the same facts and arrange them differently in different types of reference frames. And this can lead to different beliefs about those facts. So I give a simple example in the book. You can imagine I take a bunch of historical facts, things that happened, and I can say, okay, let's arrange them on a reference frame that looks like a timeline. That's a type of reference frame. It's a one-dimensional reference frame. And if I do that, I can see the two facts next to each other might be causally related in time. Like, oh, this one occurred just after that one, that maybe they're related. I can take the same set of facts and arrange them in a different reference frame. Think about like a map. And I put these events on a map. And now I can say, oh, I can say these two facts happened right next to each other in space. Maybe they're causally related because they're next to each other. Or these facts occurred next to mountains, and maybe they occurred because they were next to mountains. The point is, you can take the same set of facts and arrange them differently in different reference frames. We can all agree on the facts, but people might view those facts differently. Now, it turns out in the brain, these reference frames are not set in stone. They're discovered. They're part of the learning process. You're not aware you're doing this, but they're part of the learning process. So two people can take the same set of data, the same facts and information, arrange them in different ways, in different reference frames, and they will make different predictions, and they'll have different beliefs about those things. That can be very good at times because it can mean like two people can look at the same things different ways and they can help each other, but it can also be a problem. Sometimes you can arrange things and it's not a useful way of arranging them. Now, as I said a moment ago, some of your columns get direct input from the senses. And these columns, I highlighted here from the skin and the eyes and the ears, when they build models, it's hard for those models to be wrong. So for example, if I touch a coffee cup and you touch a coffee cup, if one of us built an incorrect model of the coffee cup, we very quickly find out because our predictions don't work out right. It's like if I think the coffee cup is round and you think it's square, well, one of us is going to be wrong. And as soon as we start touching the cup, one of us will find out that, hey, it's not round or it isn't square. So these columns can verify their predictions all the time. So two people, no matter where you live in the world, we're all going to have similar ideas what a coffee cup looks like. If we're given a coffee cup, we'll form a similar model of it. Or if we're given something, a cell phone, we'll form a similar model of it. But then there's a lot of parts of the brain, in the cortex, where they're getting inputs from other columns. They're not directly sensing anything. In fact, much of what we learn about the world is coming through language. And if we learn through language, I can't directly verify that it's correct. So we build a model of the world that may be consistent, but it may not be accurately reflected in the world. I'll give you two examples, or just a two-part example. I've never been to the city of Havana, but I believe it exists. Why do I believe it exists? Because I've read about it, and people have told me about it. I've never been there. I've never verified that it exists. I've never even seen Cuba. So, but I believe it's there because I have read things about it. I don't believe heaven exists, but some people do. And they've read about it too. So who's right? Maybe we're both right. Maybe we're both wrong. The problem, this is an inherent problem of the way the brain works. If we're learning things through other people, through language, we can form very believable sets of knowledge that are consistent with each other, and yet they be completely different and wrong. Or some could be wrong, some could be right. And this is an inherent problem the way the brain is designed. Of course, the scientific method is the way we have to suss out these false beliefs. We just keep looking for more evidence that contradicts our beliefs. But if we don't do that, and if we're not exposed to it, well, that's what we're going to believe. And so these two methods for how false beliefs can arise. One is we can take information, arrange it in different reference frames, which means we have different beliefs about the data. And the other thing is we can form beliefs based not on direct observation, but through language. And that's very useful in general, but it also leads to false beliefs. So in summary, we can talk about, this is basically what I'm talking about here. The neocortex learns a model of the world. That's the first thing you need to know. We're beginning to understand exactly how this model works in details, how the neurons do this. It's a distributed model, so it's not a single model of the world. We have thousands and thousands of sort of submodels for everything. And those models are built on reference frames in every cortical column. And that's how knowledge is structured, in reference frames. The brain's model is our reality. It's what we perceive and what we believe. And it's very, very, if it's wrong, what we believe is wrong. If it's right, what we believe is right. It turns out, we can't really sense the entire world. We can't know what the world really is like. The world is much larger than we can sense. We can only sense small parts of it. So in some sense, our model of the world is always an approximation of the real world, which is okay. It's usually pretty useful, but it can be wrong. And so our model and beliefs can be wrong. And I've talked about two ways that can happen. You can arrange the same facts in different reference frames, which could lead to different beliefs about those facts. And you can rely on facts we get through language, not direct observation. And that basically then we can build a model of the world that doesn't actually reflect the real world, but we can believe it anyway. So that's it. But end here again, a plug for my, I think here, am I at the end here? Oops, there we go. Plug for my book. I would like to say that I'm not really caring about selling books, but I really care about selling these ideas. I want everybody to know this stuff. I think everyone should know these things. In the book, I argue that we should be teaching these kind of brain theory to kids in high school in the same way we teach them about DNA and evolution, because I think it's important we all understand how it is we form beliefs about the world. The book covers a lot more than I talked about today. It's a whole section on AI and has a whole section about the future of humanity, how to think about humanity when you think about it as building a model of the world and how our knowledge is stored. How would you might think about a future that might be a little different than you might have thought about in the past. So I'll leave it at that. And that's the end of my talk. And I think we're going to do now Q&A for those who'd like to do Q&A. I'm going to stop sharing my talk here. And we're back to looking at beautiful Leanne.
Oh, thank you. Thank you. Yes, we most certainly are going to do Q&A right now. But you said a couple of things. Thank you for sharing that opening story about Richard Dawkins. If we don't, one of the lessons that people should take away today is that if you don't ask, you don't get. And you were brave enough to go and ask and get that. So yeah,
I'll admit I was nervous. Yeah.
Yeah. So you were nervous. Oh my gosh, you of all people. So that should inspire you guys, shoot your shot, if you are a Hamilton fan. I love the example that you gave of, Havana exists, but you've never been there, and how some people, feel the same way about heaven. I'm in the middle. I feel the same way about Hogwarts, although I have not been invited.
I want to believe Hogwarts is real.
I do. I want to too. I've been waiting for my owl now for a few years, and I hope the Sorting Hat puts me in Ravenclaw for sure. And I will say that the scariest thing I heard you say today, other animals have a cortex. My cat has a neocortex, and my cat's been telling me that this whole time, and I have not been believing him. So you have proved my cat correct. But man, thank you so much. And we do have several questions, but I have a few questions for you too. You said that I want to, if all the areas of the brain are the same, I started to picture it like Legos, because Legos are the same, more or less. Maybe I'm wrong there. I don't know. And are they interchangeable? Can they be used to repair a damaged section of the brain?
Yes, they can, and they do. So first of all, just take someone who's people who are born blind, congenitally blind. The part of their cortex that does vision ends up doing something else. It says, okay, we're going to do touch, or we're going to do a higher sense of touch, or we're going to do some other things. So that's one example. Another example, if you have damage, trauma in your life, let's say someone, you have there's some famous examples, but let's say you have a stroke and part of your cortex, the small part of your cortex dies. Not a big part, but the smallest part. Well, immediately you'll have some loss of function. And it's very well known that over the next 4 months or so, you'll gain a lot of that function back,
Okay.
right? And what's going on literally is that the dead section's not becoming rejuvenated.
Okay.
But what's happening is that the columns around it are taking over, and they're reassigning themselves to the part that was lost. And
Okay.
so, and they literally can say, well, I can take over that part of this. I can take over this. And there's sort of a competition going on. And then finally, there was an interesting experiment that someone did, a guy named Bakirita, and they took ferrets when they were in the utero, before they were born, and they rewired the optic nerve from the eye into the part of the brain that I think did hearing or touch or something like that. And the animal grew up, and then literally those parts of the brain took over different functions. So they're proving the Mountcastle's proposal that they can do anything. It's plug and play in some sense. It's not exactly like that. There are differences. There are reasons you wouldn't want to do this. It's not like, oh, you're just a bunch of Legos. But the basic idea is right.
Okay, thank you. Yeah, actually, and me and Mary Throop sort of had the same question that you answered about what happens to the regions of the neocortex that are supposed to be set aside for vision and hearing if the person is born blind and deaf. So you're ahead of the curve, because
Yeah.
I was also wondering, is when you did the cup demonstration, is that how Helen Keller was able to learn?
Well,
Uh,
what's interesting about Helen Keller and fascinating, right? So she was deaf and blind, right? It was really
right.
profound deficits, but she could only learn through the world through touch. And like in
Hmm.
touch, I mean, smell and taste, but we don't really rely on smell and taste very much for humans. So mostly through
Just
touch.
just just for dating. Just for dating. Right.
And women probably, the guys don't notice that stuff. Um, uh, but but she learned to model the world just like you and I model the world. Yes, she wouldn't know what
Okay.
color was, but she could walk around the world. She could speak. She gave lectures all around the world. She knew how things in the world work just like you and I did. She had knew what coffee cups were, and so it shows you that we can learn to model the world through different senses, but we end up with the same kind of model. Because the model is what the world is, and so yes, you can learn a model through touch. You can learn a model through sight, and yet learning through sight, I won't be able to detect, let's say, temperature or texture. And learning through touch, I can't learn any colors, but other than that, we can learn the same models. It's amazingly flexible system.
Yeah. And I really hadn't thought of it that way, which is why I'm here. I have the best job. Carolyn wants to know, how do the columns communicate with each other? Did you touch on that? Did I miss that?
Yeah, well, I talked about the voting. Remember?
Okay. Okay.
Well, it's more complex than that too.
Okay.
Columns send information to each other. So one column, there are cells in each column that get input, and there are cells in each column that create output. And so columns will send their output to other columns, and they'll get input from other columns. It's a very complicated system. I didn't really talk about that much. But you can just imagine them being wired together in a sort of a chain. So there's two types of connections, like, it goes to the region 1 to region 2 to region 3. That's one type of connection. And then that's like the feed forward connections, you might call it, and the feedback connections. And then the columns are also connected through these voting layers. And that's what I talked about. So there's a lot of connections going back and forth, but still almost all, like the vast majority of connections in the brain, in the cortex, are within each column. And the number of ones that go long distance into other places is still high, but it's a much smaller number.
Okay. Um, Fred wanted to know, are frames stored in one column or multiple or elsewhere? Because you
Every
said the knowledge of the cup is everywhere,
Yeah, was
but
every column is creating its own frames. Um,
oh, okay.
really, every column, and it's a very interesting way they do it. We actually know a lot about how they do this, but every cortical column has its own set of reference frames, and the next column over has a different set of reference frames. They can coordinate, but basically they create them independently. For those who are like neuroscience geeks, there's a type of cell in the old brain called the grid cells, which some people who got grid cells and place cells, these are people who got Nobel Prizes for discovering these. They're not in the neocortex, but we have speculated that these cells learn reference frames. We know this. And we've speculated that the equivalent cells exist in the neocortex. And so we know a lot about the neural mechanisms. And now we speculated this like 5 years ago, but now there's a lot of evidence this is true, that people are finding these grid cells, which are like reference same cells, throughout the neocortex. So that prediction is being verified right now.
Okay, thank you. Larry Holman wants to know, does our brain try to fill in the gaps in knowledge to form a more coherent theory or frame?
Oh, absolutely. Um, you know, it's well known. For example, everyone knows about like the blind spot. You know, you ever done that trick? Like, there's a blind spot where your optic nerve leaves the eye, and so if you look at if you put these two dots in front of you and you look at one dot, this other dot disappears. Anyway,
Oh, yeah, yeah.
there's holes in your retina. Your retina is not like a camera. Your retina has these blood vessels going through it and all these holes in it. It's a real mess, and you're not aware of any of this, right? And the reason is because the filling in, if you will, is that voting layer, right? The vote, they all say, yeah, we're looking at a cat, and so you're not aware that you're not actually. This is back to sense. Remember, I said you're not really perceiving the world; you're perceiving your model,
Yes.
right?
Yes.
Because what you're getting from your senses is this mess. It's got holes and things missing all over the place. It's like when I touch the cup. I'm not touching all of the cup, right? I'm just touching a few places, but I perceive the entire cup is there. And the same thing's going on with your
Mm.
vision. So yes, the reason it's filling in, it's less that it's filling in. It's more that your model says the cup is solid, and therefore that's what you perceive. When in reality, the input coming into your brain is full of holes and it's noisy and it's messy, but you're perceiving the model. You're not actually perceiving the real thing. I know that sounds weird, but it's true.
No, listen. I'm here for the weird. I am. John Manager. I hope I'm getting that right, John. How does consciousness fit into your models?
Yeah, I wrote a chapter about this in the book. And I know consciousness is such a controversial topic that I snuck it in the machine intelligence section. And I stuck
You
it
put
in
it
there.
in with Skynet. That's
Well,
awesome.
I said to myself, can a machine be conscious? And that sort of somewhat diffuses all these emotional arguments about consciousness, because I said, well, let's talk about a machine. Could it be conscious? Um, and the problem with consciousness is there's really no good definition for it. And lots of people think, it's all over the map. But I do address two aspects of it, and it's too much to answer here in the Q&A. But
Okay.
I talk about how our theory does explain why you have a sense of self. Why do you feel like you're present in the world? Why, like, why am I, how come I don't, am I just a machine? Why do I feel like I'm not just a machine? Um, and then the other thing is, I talked about this briefly, is like, why do we perceive things that are called qualia? Like, why do I perceive something to be green? Green is not really a thing in the world. There's light frequency, but that's not green. Why does it feel green to me? And you can explain these two things. At least I showed how one might explain them.
Right.
And so, yes, the theory does tell you about that in terms of it's part of the model again. Um, Green is part of the model of the world, and why it looks like the way it is. So it's
And,
too much for today, but yes,
right. No, I get it. And in the words of the immortal Kermit the Frog, it is not easy being green. Uh, for sure. Um, I don't know if this gets to sort of airy fairy or woo, but are you making a distinction between the mind and the brain?
No, it's all one, right?
Okay.
So I think the CFI crowd should hopefully be unanimous in this. It's in our everyday language. All of us can't avoid saying like, "Oh, well, I thought this today," like I'm not, something else. But in reality, of course, it's not like that. The brain, every thought you have is a brain state. It's neurons active. Neurons active leave the brain states. You need to you activate your neurons. That's what you're thinking. There is no separation. There's no dualism. It's all one thing, and there's nothing wrong with that. That's pretty cool. Some people are disappointed in that. They go, no.
Gary wants to know, and this is again in that same category. Any idea about dreams? About how are they created?
Yeah, it's a great.
Aside from drinking vodka way too late, or that might just be a very personal experience.
Uh, oh, well, okay. So look, there's a lot of research on dreams.
Okay.
Our theory doesn't really say much about it, and so
Okay.
I should just leave it at that. Clearly, humans need a dream. It's important. It performs a biological function. There's some theories about that. The best theory I've heard is that we need a dream because it's actually a junk cleaning process. It removes these chemicals from your brain. I think that's a pretty cool idea. But
Hmm.
our theory itself doesn't say anything about that. It doesn't need it. It's more like, hey, how does a normal, healthy, alive brain work? We don't really talk too much about disease, and we don't talk about things like like dreaming and why do you have to eat certain foods and things like that. It's like, oh, how's the information process? So our theory doesn't really say much about dreams.
Okay, fair enough. How do you, and Hewitt Rose wants to know, how do you match, and let me, full disclosure, this question is way above my pay grade. I don't even know what I'm saying here. So how do you match a Bayesian model of knowledge with your highly distributed model of knowledge?
Yeah,
And those are English words, but I
well,
don't know what Bayesian model
Bayesian,
means.
I think, is supposed to be capitalized, so it's so you
Yes, it
can
is.
so
It
you
is.
can be
It is.
excused. You can be excused for not knowing it. All right, that
Thank
is a
you.
really is a very technical question. Bayesian
Okay.
is named after this famous person. Bayes is a type of probabilistic framework, and some people think about you can think about the brain in probabilistic terms. Our theory is sort of it's not adverse to Bayesian, but Bayesian, it's not really a Bayesian theory. And the way the brain represents uncertainty is not through probabilities. It's a technical topic, and I'm not going to talk about it further, but we don't believe that that's the right framework, although you can think there's lots of things in cognition you can think in terms of probabilities, but that's not really the right framework for our model. Um,
Okay. Um, Ina wants to know, first of all, she said, thank you. This is fascinating. Can you please talk a little bit about AI and the human brain and how AI acquires models from humans?
yeah. Okay. Well, first of all, there's a whole second section of the book. The book is in 3 sections, and there's a whole
There we
second
go.
section. It's all about AI. Okay.
Okay.
And I take some very unusual. I don't know if I take controversial, but I would say I would take some non-common views about AI. And so the basic principle I have is today's AI works on very, very different principles. It's nothing like what I just talked about. And most AI researchers don't think that today's AI is smart. It's not really intelligent. They're clever. They are really good pattern classifiers and so on, but they're not really smart like humans are or animals. But the brain represents a roadmap for how to build truly intelligent machines. Now we can talk about whether if you do that or not, but the main thing of one of the key messages I want to get across is that when we want to build truly intelligent machines, and just disclaimer, I think we're going to be doing this in big time at the latter part of this century.
Okay.
So we're going to have these. It's going to like crazy, but when we build these intelligent machines, we don't want to build the entire brain. We don't want to build the old parts of the human brain. We don't want them to be sitting around going donuts. Oh, I'm lazy, whatever. So yeah.
I think that was a scene out an outtake of iRobot. Yes.
Yeah,
No,
maybe. I don't know. So you can build an intelligent machine by replicating the neocortex, and on its own, the neocortex does not, it can be smart, but it has no motivations. It's not like going to say, oh, human, you've created me. Now I'm going to take over because I'm tired of being, your slave. It's not going to do that.
Okay.
We have to give these intelligent machines some motivations or some drives or some things that they have to do, but they aren't going to be like us at all unless we went out of our way to do that. And so a lot of people think that AI is an existential threat to humanity. Like we're going to create these super intelligent machines and they're going to kill us or enslave us and things like that.
Yes.
I don't believe that's true at all. And I walk through arguments about that. So the whole section goes through all these issues about intelligent machines, what they'll be like, what they won't be like, and why today's AI is not. I have a chapter called "Why There's No I in AI," because today's AI is not intelligent.
Got it. No, that is comforting, and you know where that's coming from. There's a bit of a Venn diagram and a crossover of folks who are here and folks who have watched way too many sci-fi movies, and we've been primed for how our phone is going to take us over.
Yeah, well, and a lot of smart people are out there claiming that the world is going to be, overrun by intelligent machines. I mean, a lot of people are saying this now. I don't know if you know that, but I think they're all wrong, and I make a very reasoned argument why.
And yet another reason, a shameless plug for why you guys should get his book. Thank you so much for spending time with us and sharing your time and expertise. And I thank everyone in the audience for watching. And I'm so sorry I couldn't get to all of your questions. There is never enough time to do that, but I got to as many as I could. And I do want to assure everyone, if you've missed this, anything, the recording of this event will be available tomorrow at skepticalinquirer.org. And our reminder, our next guest in this series will be here on Thursday, April 29th, Mick West, talking about escaping the rabbit hole, how to help your conspiracy theorist friend. I will be here with pen and paper, taking notes in hand. So my thanks, of course, to Skeptical Inquirer, CFI, our producer tonight, Mark Kreidler, and to you, the audience. And again, to you, Jeff, thank you for making the time and
Thank you for
sharing your
having me. It was
expertise.
great. Great.
Thank you. And everybody, you know me. My name is Leanne Lord. Thank you and good night. Good night, Jeff.
Good night.